In this video, we're going to discuss the standard rings that we expect when we cyclize a sugar. So we have a Fischer drawing here of an aldose hexose. When you turn it into a ring, there are two standards. There is a furanose, which will be a 5-atom ring. 4 carbons, 1 oxygen. There's also a pyranose, which is a 6-atom ring. 5 carbons, 1 oxygen. The vast majority of time when we cyclize a sugar, it takes one of these two forms. Well, that rightmost carbon, this is the anomeric carbon. That is the carbon that was previously where the double bond oxygen was. Anomeric is actually a term for newly chiral, because once you form the ring, that becomes a chiral carbon. It isn't originally. It only has 3 things attached, but once you form the ring, it will have 4 things. We always draw that on the rightmost of these carbons in the ring. And for you to number things, on the Fischer, we'd have 1, 2, 3, 4, 5, and 6. So on our ring, that carbon, well, the double bond oxygen had been on carbon 1, so that's carbon 1. 2, 3, and 4. On the pyranose, 1, 2, 3, 4, and 5. You can correlate the Fischer diagram carbons to the ring by always setting up your rings this way. And so we always draw our furanose and our pyranose in this fashion. The oxygen on top, and the rightmost carbon of the ring being the carbon that used to have the double bond oxygen. Each of these positions is going to have an up and down. And so we can install the up and down that we expect on each of those carbons. And we can identify, well, which thing goes where. Carbon 2 and carbon 3 both have their OH on the right. When you tip over a Fischer drawing to turn it into a ring drawing, any right side OH will be down in the ring. And so carbon 2's OH will be down. Carbon 3's OH will also be down, and that'll be true for both the pyranose or the furanose. Carbon 4 is where we run into something different, because on the pyranose, 4 is just part of the ring. And so it has its up and down, and an OH is still attached. It was originally on the left, and so a left OH is going to be up in the ring. But the problem with the furanose is that you can't do that. Carbon 4 has its oxygen closing the ring. It's actually oxygen from carbon 4 that attacks to make the ring for the furanose. As a result, there is no OH on carbon 4 for the furanose. It is used up in the ring. The only thing still on carbon 4 is the hydrogen and the other carbons, all the extra carbons that aren't part of the ring. Well, there's an up and down for those. If the OH group that makes the ring was on the left, if it's an L, then your extra carbons will always go down. So carbon 5, carbon 6. If your OH that makes the ring was on the right, if it was a D, then your extra carbons would go up, which is what we'll actually see over here in the pyranose. In the pyranose, it's carbon 5 whose OH is making the ring. So carbon 5 doesn't have an OH on it anymore. It got used to make the ring. The other things on carbon 5 are a hydrogen and carbon 6. And so the up and down is going to consist of a hydrogen and carbon 6 Well, because the OH was on right for carbon 5, because it was D, the extra carbons go up. So carbon 6 is up above, hydrogen's down below. Carbon 6 has 2 hydrogens and an OH. And we can add those bits over here on the furanose as well. You can translate your fischer into a furanose or a pyranose ring, regardless of what your fischer is, by just remembering these steps. A furanose ring will always be 4 carbons and 1 oxygen. A pyranose will always be 5 carbons and 1 oxygen. The rightmost carbon of the ring is the carbon where the double bond oxygen used to exist. You can then number all the rest of the carbons in your ring, and then just say, well, where were my OHs, on the right or on the left? That'll tell you if it's down if they were on the right, or an up OH if they were on the left. Tricks: remember that if your carbon is the one attached to an oxygen making the ring, so carbon 5 over here in the pyranose and carbon 4 over here in the furanose, you don't have an OH anymore. Your OH got used to make the ring. So be careful not to try to draw an OH on carbon 4 of the furanose. It doesn't have one anymore. This is a general idea of a furanose and a pyranose. Now, carbon 1 for both of them. Well, that we didn't have. There wasn't a right or left OH. There was no chirality originally. When you form the ring, you can do both. You could either have the new group you make, because remember, if you have an aldehyde and you add an alcohol, what you get is a hemiacetal. Because our OH at carbon 4 attacks the double bond for our furanose, we are going to create an OH at carbon 1. It can either go up or it can go down. It can be either. Depending on how you attack, you will get both the up and a down. If you're up, it is a beta. If you're down, it is an alpha. If you are just told to make a furanose, you can do either. It could be beta or alpha. But if you were asked specifically to make a beta furanose, then you would need that OH on the anomeric carbon to go up. If we wanted an alpha pyranose, well then, over on carbon 1, we're going to put the OH down. And so if you're just told pyranose, the OH could be either up or down. But if you are told it's alpha, then you know that anomeric OH is down. Well, this is great for aldehydes, but you can also do this for ketones. So if we have CH2OH, ketone, let's do the beta furanose. So we're going to convert this ketose into a beta furanose ring. Give it a shot. Go ahead and pause. See if you can solve this, and then come back and we'll walk through it. All right, if you're back, well, it's a furanose. So to start, we just make the standard furanose ring. Don't need to know anything else. It's going to have this carbon set. I have my anomeric carbon. Well, that is right here. That's really carbon 2. And so that's 2, 3, 4, and 5 going around our molecule. Coming off each of those spots, we'll have something up and down. And so now we have to determine what goes up and down. Well, for carbon 3, the OH was on the right, which means it is down in our ring. Carbon 4, the OH was on the left, so it is up in our ring. Carbon 5, well, there's no more OH. Carbon 5 is the one whose oxygen made the ring. So there is no OH on carbon 5. There is, however, a hydrogen and an extra carbon. Since the OH that made the ring was a D, it was on the right side, our extra carbons will go up. So there's a carbon there. Carbon 6 is up. We don't need to actually write it in. Often we'll just do the skeletal drawing. So the carbon 6 goes up. And the last bit is carbon 1. Well, carbon 1 we said has to be beta. So OH will go up. But what's down? In the aldehydes, the other thing was a hydrogen, but that's not true here. We have a ketone. The other thing is carbon 1. So carbon 1 is down here, which is really just a CH2OH. Make it look like our other one. And so in this case, the rightmost carbon of the ring is not carbon 1 because it was a ketose sugar. All that means is that our beta is still the OH on the anomeric carbon is up. Anything past, so all of carbon 1, must be down. And so by following these rules, we can turn our ketoses or our aldoses into our furanose and pyranose rings. We simply have to set the original furanose or pyranose structure, determine what number atom is the anomeric, and then assemble all the other positions based on those numbers.